Hi, so there were some questions about some carbohydrates, their numbering, and some labeling. So I'm going to run through that. So the first thing that I want to talk about is I want to talk about the numbering system. So just as a reminder, we kind of went over this in class, but that you start the numbering based on the location of the of the chain, but where the aldehyde is. So this is carbon 1, 2, 3, 4, and 5. In this particular case here of glucose, we have 1, 2, 3, 4, and 5, 6. Over here in fructose, you can see that the ketone is it's here, it's at number 2, but we go above that, right? So it's carbon 1, 2, 3, 4, 5, and 6. All right, so hopefully you understand how to number them. The next question I want to go over is which of these carbons are chiral? So looking at ribose again up here, so carbon 1, is it chiral? No, because this one has a carbon attached to a hydrogen here, a double bond oxygen, so right there makes it non-chiral. Is carbon 2 chiral? Yes, because it has this alcohol group as one group attached to it, an H, a CH, a double bond O, and then this other R group. Is carbon 3 chiral? Yes. Is carbon 4 chiral? Yes. Is carbon 5 chiral? No, because we have 2 hydrogens attached to it. So if we're looking down here at glucose, same question. Is carbon 1 chiral? No. But 2, 3, 4, and 5 are all chiral. Carbon 6 is not chiral. So that's the first thing that I wanted to mention. And again, just as a reminder, the blue here is the aldehyde or the ketone group. Now, with it being chiral, it's asymmetrical, right? And so what you see in red is this is the carbon that is the furthest from our aldehyde or our ketone that is still chiral or asymmetrical. So it's highlighted here in red. So you can see here on glucose, it's on carbon 5. This carbon, the one in red, determines whether it is D or L. So I'm going to make you think back to your protein and your amino acids. And if you remember, all amino acids are in the L formation because they're to the left. But if we look here at carbon 5 on glucose, where is the alcohol group? It is to the right, making this a D here. So again, D just means to the right. And which one do we determine? It is the carbon that is the furthest from the aldehyde or ketone group. So if you look here, it's to the right, to the right, to the right. So these are all in the D formation. I would say 98% of the time the carbohydrates are in the D formation. There's only on a rare occasion that it's in the L formation. The other component that we seem to be having issues with is what occurs in making this go from linear into a ring structure. So again, the two highlighted here in blue and in red are going to become important. So here's glucose again. So what's going to happen is that we have this alcohol group, and this is the alcohol group on the furthest carbon that is asymmetrical. So on the carbon that determines whether it's D or L, that's the carbon that has the alcohol group attached to it. That's why this one's so important. That's why this one determines D and L. That's the alcohol group that's going to attack our aldehyde or our ketone, and it's going to produce our ring structure. So here's our ring structure. Now, going back to chiral versus non-chiral, we said before that number 1 is not because it has this double bond, but 2, 3, 4, 5 all were. Now, after we go through this ring structure, here's carbon 1 again. So carbon 1 now has a hydrogen attached to it, an OH group attached to it, an oxygen group attached to it, and this other carbon attached to it. So it has now become chiral or asymmetrical. And because it has become asymmetrical, it is this new chiral center. So this is the only one that has changed. Number 2 was chiral before and it's still chiral. Number 3 was chiral before and it still is. Number 4 was chiral before and it still is. And number 5 was chiral before and it still is. So the one that's added is our carbon 1, and this is known as the anomeric carbon. Okay. The only other component that I wanted to add to this lecture note is that we had questions on what is alpha and what is beta. So what alpha is doing is when the OH group is down, so this hydroxyl group is what's considered in the trans position. And so it has this alpha formation. And it's trans to this oxygen, right? So oxygen is up, so this alcohol group is down, making this an alpha. If you look here at the beta, the OH group is up. So this is now in the cis formation, so they're on the same location. These two oxygens are next to each other. And so that is considered the beta formation. So if we look here at this glucose, this would be an alpha, right, because it's down in correlation to the oxygen in this particular format. And so this is going to be our alpha. And actually, there's a better picture right here. So here we have an alpha. So again, this is where that OH group was, and this is how that glycosidic bond is going to be formed. Here you can see that we have the alpha group over here, so we see that's down, and then look, we have this beta group, and if you look, you can see this really kind of odd structure, and that's because the OH group was up in order to form this as you go through. Overall, I'm really just concerned about knowing, you know, up versus down, alpha versus beta, really in just one singular ring structure. I'm not going to ask you to name, you know, scientifically name a disaccharide, but I did want to mention that. The other thing that I wanted to just mention is that when we do make a disaccharide, you can see that it's the anomeric carbon of one monosaccharide is going to attach to an OH group of another monosaccharide, and that's going to help form our glycosidic bond. Hopefully that answers your questions. If you have any more, let me know. Thanks.